So our last speaker, Kumar, is coming here from Google, and he's going to tell us about how to use learning and machine learning in online analytics.
Thanks for this. Hope you can all hear me. Hi, so I'm Ravi. I work at Google in Mountain View, and I'm going to talk about parsimonious learning augmented algorithms. This is a line of work that we have been doing for the last 2 or 3 years. And this is like a slightly new resource measure that we want to introduce in this space. And this is joint work with Aditya, who's in the audience somewhere, from Utah, and Ashok, who's faculty at BU, Sangjin, who Ben also mentioned from Merced, and his student, another Aditya, and then Manish, my colleague at Google. So just stop me at any time if you have any questions. So the topic that we'll focus on today is online algorithms. So Ben already introduced the notion of learning augmented algorithms, but I want to restrict that attention to online algorithms. So I'm sure most of you know this topic quite well. It's a great way to model decision making under uncertainty. The setup is the following. So you have inputs to the algorithm arriving one by one, and you have an algorithm, and the goal of the algorithm is to make a decision that's irrevocable. So you have these inputs here, and you have the algorithm, and the algorithm makes some decision. It can be a very general decision, but it can't undo what it made. That's what makes this problem challenging. And I would like to think of handling the unknown. Remember, it's an online algorithm, so we don't know much about the future. So the whole notion of handling the unknown falls into one of 2 rubrics. I would like to cover them. The first is what we are familiar with a little bit, assuming the audience is primarily computer science, combinatorial optimization people. It's a field of online algorithms. So the biggest assumption the online algorithms make is that the future inputs are completely unknown to the algorithm. Therefore, they have to assume the worst possible case of an adversary, an active adversary, trying to disrupt the performance of the algorithm. So therefore, they tend to be very pessimistic in nature. The bounds, the way they behave in practice, or even in theory, are very pessimistic because they have to assume the worst case. In fact, most of CS is on worst case bounds, theoretical CS, and therefore it's of that format. Okay, they're pessimistic in nature. And that very property makes it very hard for online algorithms to exploit patterns in the data, because these are worst case inputs, right? So there may not be any patterns, and you can't assume such patterns exist. And so you can't even really exploit them, even if they exist. And online algorithms has been studied in various settings, like Ben was talking about matching and so on, and it's been studied typically in caching, scheduling optimization, and many other settings. It's a very, very natural model that people have worked with. In contrast, there is another body of a research community that deals with uncertainty or handling the unknown. That's machine learning. The primary premise in machine learning, at least if you want to summarize it in a sentence, is you want to be able to exploit the data or history from the past. How do I take what has happened in the past and somehow succinctly summarize that into a compact description and use that to predict the future? That's how most machine learning operates. So there, the goal is to build models that are robust, that don't really focus on small portions of the data, but try to generalize or try to identify patterns that are broadly across many settings, and use them to predict the future. That's another body of work that's happening there in machine learning. So the properties they tend to have is good on average performance. ML models, we all know, they work pretty well in practice. So they most practical instances are not really adversarial or worst case. So they tend to be pretty good on average performance. Unfortunately, they are also less robust outliers because they learn the average behavior. So if you supply them with some worst case inputs or inputs that don't really fit their expectation, then they can make really egregious errors. We all know all the worst case examples that come up with machine learning. Okay. And the kind of things that people have looked at in this setting is you can deal with predictions, like which page is occurring next in a caching algorithm, or which job is going to be, how long the job is going to run, and so on. So that's the kind of a setup that happens in machine learning. And what we'll try to address is how these two things can come together, and that's the whole goal of the learning augmented study. Okay. So before we go into that, I would like to introduce a couple of performance metrics. Again, like most of you are familiar with this, but just to set the terminology straight. One is the competitive ratio, and it is a classical measure that's used in online algorithms. The goal of this measure is to measure the performance of the online algorithms with respect to an offline algorithm that knows the entire history of the inputs. That's the quantity that they are usually interested in. And it usually tends to be like a multiplicative quantity for most purposes. And it's used in more combinatorial algorithm setting. On the other hand, there is another quantity called regret, which is used in online optimization mode machine learning settings, where you measure the performance of an algorithm against a class of benchmarks. You fix a class of benchmarks. We'll see an example of that later. And you measure how well your algorithm that you design does against this class of benchmarks. And the performance is usually expressed as a difference. You take the difference between what your algorithm, the cost of your algorithm, if you can call it, and the cost of the optimal algorithm, the benchmark, and express that difference. And that's usually called the regret. Okay? And it's an additive quantity, and it's used in machine learning settings. So we'll touch upon both these quantities at the top. Okay, now that we have set up all the necessary background, so what do learning augmented algorithms try to achieve? Okay. So the main goal is the following. Can one improve the performance of online algorithms when there is some possibly wrong information about the future? So you have this algorithm, remember online algorithm, your inputs arrive in one by one, and you have this algorithm sitting there, and you would like to know if there is a prediction or an advice or a hint or some form of indication about the future is available to the algorithm. Can that be exploited in a provably good fashion? That's the goal of this setup. Okay. Okay, so I view this problem space of learning augmented online algorithms consisting of three main cogs. This is my personal view. So one is the metrics. So we talked about metrics. I'll just go into the detail later. Another is resources. And the third is what kind of hints you supply. So regarding metrics, you can either talk about competitive ratio or in combinatorial settings, or you can talk about regret in more like ML settings. Another set of aspects or another set of characteristics of this problem space is performance. What are you trying to improve, right? So you talk about online learning augmented algorithms. What is the goal? The goal could be, I want to improve the performance. Or maybe I want to improve these metrics, right? I want to get a better competitive ratio, or I want to get like a lower regret. Or it could be the case that I want to improve the memory use of the algorithm. People have looked at, in streaming settings, for example, if I know something about the future, can I use that to cut down the space required with the algorithm? So you want to focus on memory. Or like what Ben was talking about, the warm start, you want to improve the running time of the algorithm. Or maybe you can use the future to improve the running time, or maybe you can use something about the history. Right? That's the second aspect of this problem space. And the third is, what kind of hints are you allowed to have? So maybe the characteristic could be the type of hint. This is a very broad thing, because this really depends on what kind of ML model that you put there in place, right? The different ML models will supply different kinds of hints, and that can have different kinds of effects on what you can show for the algorithm, or what kind of error measure that you want to focus on. So remember, you want to tie back the performance of the algorithm to how good the oracle is. So that's another measure. Or the size of the hints, how big the hints are, like are they like just bits, or are they something bigger? And finally, another important aspect is how many times the hints get used. Does the algorithm need hint at every time step, or can it get away with a few hints here and there, right? And in fact, this will be the focus of our talk. We will look at the use of hints as an important measure in this whole space. Okay. So there are three main desiderata that you want any learning augmented algorithm to satisfy. One is consistency. What does it mean? So consistency means that we ask the question, how well the algorithms do when the hints are good, right? So you want the algorithms to achieve the best possible performance, assuming that the hints supplied by the machine learned oracle are extremely good, right? In fact, ideally, since we are in the online setting, we want a near offline performance if the hints are good. Right? That's a clear goal that we can state. But of course, this alone is not enough, right? Because remember, the machine ML oracle can supply you with really bad hints, right? I mean, just because it's not meant to handle every possible case. And that brings to the next desiderata, which is robustness. So we want almost a converse property to hold, which is the question there is how well the algorithm performs when the hints are bad. Ideally, we want the algorithm not to throw up its hand saying that, sorry, I'm going to do really badly because you gave me bad hits. That's not a desirable property. Instead, we want the algorithm to gracefully fall back to a near online performance if the hints are like very bad, even if they're adversarial. Every time the ML oracle really tries to mess around with me, even in that case, I want the performance to be degrading to like an online performance. This is remember, these are not very symmetric cases, but this is like a very strict criteria that we want to impose. And I want to state a third criteria, which is parsimony, where we want to ask the question, do these algorithms really use the hint only when they are needed and not ask for them if they are not needed? So this is again like a performance criteria that we want to impose on these algorithms. We want the algorithms to really use hints only when they need them. And of course, we want this property to hold, retaining both consistency and robustness. You don't want to sacrifice on either of these two properties. Just because you ask me to be parsimonious doesn't mean that I just ask one hint and then be done with it. We still want these two things, but at the same time, we want them to be query efficient in some sense. And why is this these two are like easily motivated, but why is this an interesting property? This is because as ML models become more complicated, we would like to make the case that it's actually can be expensive to query large ML models. So it's not the case that hints can come for free at every time, right? If the hints take a lot of computation or a lot of other resources to compute, we want to take that into account when we develop algorithms. So we want this to be a criteria that that's interesting. All right, so any questions about the setup? Thanks. Okay, so in this, with all the setup done, so I would like to focus on two results in this talk. The first, so one will be on each framework, one will be on the regret setting and one will be on the comparative ratio setting, but the end goal is very similar. Okay, so the first one I'm going to focus on is online linear optimization. It's a joint work with Aditya, Ashok, and Manish. It appeared last year in Europe. Okay, so what is the problem here? It's a very, very nice, elegant setup. It was proposed by Martin Zinkevich almost like 2 decades ago. So here's the setup. So you have, okay. So let's assume that we're working in the unit ball case. So let B sub D be the unit ball in D dimensions. Okay. And it's an interactive online game. It proceeds as follows. At every time step, the algorithm is asked to choose a vector, asked to play a vector, WT, in this unit ball. So every time step, the algorithm's goal is to generate a vector WT. After it responds with a vector, nature gets back to it with another vector CT. It's called the cost vector. And you compute the loss at this step as the inner product of the vector that the algorithm responded and the vector that the nature provided. So it's inner product of WT and CT. That's a loss at this step. And so this, I call this constraint because you want all the actions to be in this unit ball. And the objective is to minimize regret, which is defined as the difference between the cost, the loss incurred by the algorithm, which is the inner product of CT and WT at every time step, summed over all time, minus the single vector I could have played in retrospect that achieves the best possible outcome. So it's the difference between these two. Now you see this is working against a fixed class of benchmarks, right? So you're fixing a benchmark which is to be like a fixed vector in the space, and you ask how well my algorithm does against this fixed vector. That's your measure here. And the goal of this is to develop algorithms to minimize this regret. It's a very clean formulation. It captures a lot of settings, and in fact, like Ella has a book on this. So it's a widely studied study. Okay. So again, like you might know many of this, but I just want to recap. For this basic setup, there is a well-known algorithm called follow the leader (FTRL), where how would I respond, right? I mean, at every step, I'm asked to respond to a vector with a vector WT without even knowing what's going to happen, right? The best way to respond is to look at what happened in the past and try to play against that. So the algorithm chooses the vector WT with the least loss over the previous rounds, and then responds with that vector. So if the loss is like linear, then it tries to compute WT that minimizes the history loss in some sense and tries to respond to that. That's just a natural algorithm that you would come up with. It's FTRL. And it turns out actually you can improve the performance of the algorithm by adding a small regularization term instead of responding with arbitrary WT. You can add like a term that regularizes not to grow too big. And that turns out to be a well-known algorithm called follow the regularized leader. This is with a quadratic regularizer here. And the regret of this FTRL turns out to be square root t. So the holy grail in this whole study is to get a sublinear regret. And this is great. So this is all well known here. Okay. That's the FTRL. Okay. So now let's get back to how would this problem look with hints, right? So constrained online optimization with hints. And here is a setup. Identical to before, except that in the beginning, for every time step, the algorithm receives a hint vector ht in the unit bound. So in this setup, ht first comes first, and then the algorithm has a chance to look at the hint and then compose its response wt, and the rest of the steps are same as before. And then nature provides with cost ct, and then you compute the loss in the same way, the inner product between the cost and wt, and then you measure the regret in the same way. The only difference is before the algorithm plays, it has a chance to examine the hint that's provided. That's all over hints. Okay. So this looks like a very simple setup. What has been done here? Okay. So first of all, let's define what do we mean by good hint, right? I mean, here we need to define. So here, I mean, of course, now we get a hint, but I want to quantify when is a hint good. And we use the following definition. We say a hint is good if it's alpha correlated with the cost that's yet to appear, right? So ht hint is good if the angle between this and ct is at least some alpha. Think of alpha as like a small constant, alpha times the length of ct. That's what we mean by hint to be good. And geometrically it looks something like this. No, this is a hint that's unknown. This is the cost vector that's unknown, and this criteria defines some kind of a hyperplane. And so all the hints, all the vectors that fall into this part are considered good, and everything else is considered bad. That's a notion of what a good hint means. It's a very reasonable notion if you think about it. Now, all I'm asking is a mild correlation with what's going to happen in the future. Okay. And the notion of query cost, we'll use a query cost of alpha times ct squared. So whenever we query, we say that we incur this cost, regardless of this quality. We don't charge the cost only for good hints. We just charge regardless of what the hint is. So this is a query cost.
You don't observe the query cost.
No.
Because that will reveal information.
Exactly. Yeah, we don't observe the query cost, but we'll measure this as part of the algorithm's performance. Yeah.
When computing the benchmark W star with the hints case, are the hints involved in the decision for W star?
No. W star is W star.
Can you elaborate? For me, I don't understand why this is a natural query cost.
Oh, it turns out in the harder cases when the C's are large, so this kind of captures that.
Okay.
Same person.
Okay, so what's, I mean, this is not, we're not proposing this problem for the first time. I just briefly delve into the history of this. As I said, the holy grail in this problem is to get sublinear regret bound. Sublinear means, you know, the average performance approaches like a fixed benchmark. That's what it means. And the original paper and subsequent work, you can obtain regrets that are tight actually, like square root t, and then you can't do anything more than that. Right? That's in fact the random cost vectors case is a hard instance for this. You can't do better than that. Okay. So this problem was considered many years ago by Elad and Nimrod, who showed that if the first coordinate of the cost is known to the algorithm, and if it has sufficient contribution to the cost, that means its magnitude is at least alpha, then you can do substantially better. You can get a log regret. That's what they showed in 2007. So they have some dependence on like dimension and so on, how much they are correlated and so on, but it's like a result in that direction. You get a, think of this as somebody is providing you a hint about the first coordinate, and that hint is like sufficiently, you know, good, right? What it means. So fairly recently, Dekel et al. And I don't know if Nika is in the audience. So they considered a more robust version of this, a more actually consistent version of this, where they showed that if every hint is alpha correlated with the cost, you can actually still get a log regret, right? It's not something about the first coordinate, but all I care about is that when I get a hint, it has to be sufficiently correlated with the cost. So this is a consistent result. In fact, they even have an improvement over D. So this result is consistent, right? Basically, if the hints are very correlated, you get a log regret. I mean, log regret is the best thing you can do in some sense, right? But it's not robust. In fact, we don't know how to make their proof robust. In fact, if even if one step of their algorithm does not get the well correlated hint, then as far as we know, the proof may not go through. And of course, it's not parsimonious because we need the hint at every time step. So fairly recently, we worked on this problem and we made this result robust using actually different techniques. So what we showed is that same set of authors. So what we showed is that if most hints are alpha correlated, you don't need all of them to be alpha correlated. Most alpha correlated, then you can still get like a log regret. In fact, we can even improve the dependence on dimension, can make it completely go away. So this result is an improvement over this because it's now become robust. No, you know, I don't need to know which hints are good or which hints are bad. I can even deal with bad hints in some sense.
Most near B is the proportion converges to 1, or
I'm sorry?
what does most mean?
Oh, so okay, good point. What does most mean? So I've tried to drop all the dependence on the actual number of hints that are bad, but you can quantitatively relate if I know certain number of hints are bad, then that translates correspondingly to a regret. For example, if say, I mean, technically we'll come to that exact bound later, but suppose say B of the hints are bad, you get regret something like root B. So yeah, just for simplicity, I dropped all this dependence.
Do you need to know how many?
No, technically no. So, but it's not parsimonious because our algorithm does require a hint at every time step for it to work. This is the history of the problem here. So here is a main result. This is exactly what you were asking about. If there are B bad hints, then we can show an algorithm that if there are B bad hints, then it obtains a regret of square root B log T over alpha. That's the main result. So let's start at this quantity. Again, I've simplified this. The actual expression is a little bit more messy, but this is spirit of this very similar. It is consistent because suppose all the hints are good. That means B is 0. Remember, our notion of good is hint is alpha correlated with the cost. If all the hints are good, B is 0, so you get back to log T regret. Okay. And it's robust because even if every hint is bad, B is equal to T, then I mean, this expression gives you a root T log T, but actually you don't need the log. The complicated expression gets rid of the log. So you actually get back a root T. So even if every hint is bad, I suppose supply the algorithm with a random hint at every time step, still it doesn't go bad. You still get root t regret. And the expected cost is square root t. So you have like a sublinear cost of querying the ML oracle. And that's the main result that we have. Okay, so just like, yeah, sorry. Yeah, good point. Yeah, so I've tried to brush certain things under the rug, but it didn't work. So the algorithm needs to know alpha. Yeah. That's one of the open problems that we don't know how to solve.
So what if my cost is like a constant independent of the CT of the query? Like how robust is this? Is it really like dependent on that you define the cost?
I don't think it really depends. I think it's fairly robust, but I don't know if we have pushed the boundaries of it.
What's the expectation result here? Do you expect this result to be root b plus log t eventually? Or?
So that's a actual complicated expression, but I just simplified it.
And want to help on both the sides?
Yeah, pretty much every term in this is tight. I'll show the exact lower bound next. So I'll show it a little bit later. Actually. So, yeah. So what is the key idea here? It's very simple. So there are two ideas here. One is that we would like to use FTRL as much as possible because FTRL has root t regret and so on. But there are cases where FTRL might fail. Here is an example, right? Here's an unknown cost vector. And the hint supplied is super good. But FTRL gives you like a bad, it's an uncorrelated vector. So in this case, we would like to actually use a hint if possible. Right? Because we want to ignore whatever FTRL says and just use a hint. So if FTRL is unable to predict the cost, then the hint is actually better to use. Okay. So in this case, we would like to query the ML oracle, use the hint, and in a very stylized setting, by querying the oracle root t times, I can cancel off the root t regret that FTRL produces. That's the high-level idea here. If FTRL fails, but FTRL may not fail. So there are cases where you want to use FTRL. So FTRL is really well correlated with, in this case, here's unknown vector cost, and here is the output of FTRL. It's really well correlated with the cost. In which case, I don't want to use a hint, because it's a waste of a query in some sense. In this case, we want to use FTRL. So in fact, using the hint, actually the hints are bad. Using the hints may actually hurt. We don't want to use that. But in this case, how do we control the regret? That's a basic question. And in fact, the bigger question is, how do we detect which of these two cases we are in, right? We don't know, because everything is unknown here. Okay. So it's a mild another aside where it turns out that the question that Ola asked, if the costs are sufficiently big, okay, then it turns out it's actually an easy case for FTL. So in fact, FTL and therefore FTRL also achieves like a log regret. It's done by a work of Huang et al. So if the costs are big, then it's kind of easy case for FTR. So can modify their analysis to show even for FTR. So you want to keep this result in mind somehow. Okay, so here is the, I won't go into the details of the proof, but I'll give you a high level idea. Yeah. Intuition. I don't know if I can explain it in a short way. Maybe Aditya, do you have any intuition?
I guess the optimum changes very slightly from iteration to iteration. So
if you go back, can you go back?
Your regret is much better. So
but it's a norm, it's outside the sum, right? So it's that they are correlated.
They're correlated, yeah.
So some change very.
Yeah, we can take it offline. Okay, yeah. So here's our outline of the proof. So again, we have two cases where the hints are really good. So they kind of remove alpha minus alpha factor from the total regret. Okay. In this case, we would actually query the oracle root t times to remove all the regret. That's one case. And case two is when FTR itself is just better than hints on average. And the main thing that we show is that if this is the case, then it implies a condition that I put in the last slide. So basically, it means that the total sum of all the costs is actually sufficiently large. And as Aditya was saying, that actually means the op doesn't move much, and therefore you get like a log regret. These are the two cases that we need to handle.
How do you detect them?
Yes, exactly. How do you detect them? And for that, so that's the main question, right? How do you detect this on the fly? And the main idea here is to use another online gradient descent step to decide which of these two cases you're on. So it's like a box sitting on top of these two things. So overall, this is how the picture looks. So you have what we call a hint probability chooser. Basically, this module decides whether you want to query for hint or not. So or it is a one-dimensional online gradient descent problem with some small modification. So it decides and tells you with probability PT choose a hints. And then you flip a coin. And if it says false heads, you ask for the hint and choose a hint. And if it falls tail, then you use a standard FTRL. And then you ship the loss to, of course, send the standard CT to FTRL, but you ship this loss of using this PT back to the hints probability chooser. So basically, it's a recursive construction where this step decides which case you are. That's the main idea here. But again, some technical details are involved, but I won't go into that.
So is the gain in parsimony at the cost of perhaps more computation?
I wouldn't. Yeah, I don't know. I mean, I don't know how to quantify the cost of computation here. I kind of assume that everything is like linear or in this vector size. Yeah. But the thing is, the thing to keep in mind is that for this to work, we do exploit a lot of structure in the problem, and it's not like a simple any OGD. It has some structures that I'm not going to detail, but those things enable these things to be put together. The structure in the problem that. But anyway, this is the high-level idea.
Sorry, what do you send to the left level? You said difference between
exactly. Yeah. Only this. Now, basically, the loss of using the hint versus loss of using the FTRL. Basically, it's a hint to this probability chooser that which of these two cases I am in, right? And that updates the PT based on the feedback it receives, and then it iterates. So that's what it is. It's a one-dimensional problem. So just send this value. Okay, so that's a entire algorithm, and so lower bounds. So this is the bound that we put. In terms of that, pretty much everything is tight here. So you do incur a regret of square root b, where b is the number of bad hints. You need this factor 1 over alpha. You need the log t term, and you also need square root t. Initially there was some hope that maybe you can get an elastic result, where I can control the amount of queries I make versus the regret I get. But if you query less than square root t times, then you can create instances where you get square root t regret. So basically, it's a very sharp threshold there. Okay. So that way. And in fact, even more interestingly, any deterministic algorithm, there's a randomization step there, right, to pick. In fact, any deterministic algorithm that gets log regret will use like essentially linear number of hints. So there's another interesting separation here between deterministic algorithms and randomization. And I didn't cover this, but this is in contrast to some results that we have in the paper on unconstrained version of the problem. So there, it turns out that a deterministic algorithm can get you like a log to the 3/2 regret. Okay, so in the interest of time, I wouldn't go much into the lower bound. So the lower bound is essentially, the standard hard instance for the online optimization setting. You can set up a bunch of costs and hints where the expected loss of any algorithm is 0. It's like a mean 0 case. And then you can show that if you supply with all 1 hints, then you can express the entire regret in terms of number of times it's bad, actually. So it's a dependence on B's type. Okay. So this is all I had to say about online optimization. So before I ask you to forget about regret and then move to competitive ratio, any questions? Yeah.
Have you looked at the
delays, like if the computation of the hint itself is so expensive, I imagine you wouldn't receive it like instantaneously, right?
Yeah, we have been assuming that we get instantaneously, but delay in the present request. Okay, so I wouldn't call the second part, maybe the last 1/5 part of my talk is online caching. It's a joint work with Sangjin, Aditya, his student, and Manish. It appeared this a couple of months ago at ICML. So I don't need to motivate caching that much, but I just recap quickly. So you have the setup as online setting. You have a cache of size k, and you have page requests coming at every time step. And the goal is to access the pages from the cache, right? And you incur a cost if the page that is being requested is not in the cache. So the goal here is to decide which pages live in this cache. And of course, if I know the entire future, if I know the entire sequence of requests, then there's a very famous, well-known algorithm of Bellardi that gives you the optimal solution. So the question is, how well your algorithm can compare against this optimal solution in terms of this multiplicative factor, which is the comparative ratio. That's an object we study here. And with hints, the setup is exactly same as online optimization, except that the hint we get before the algorithm decides is the next arrival of this page. Now, it's a very strong notion if you think about it. So when I see a page, I also get a sense of when is it going to appear next. But let's work with this simple thing. And based on this hint, I need to decide which pages in the cache which page in the cache I need to throw out in case I need to incorporate PT into the cache. And same, everything else is the same. The notion of comparative ratio, everything is same, except that I get a hint about the future arrival of this page. Okay. So caching with hints captures like many settings in a nice way. So if the hints are completely error-free, right? If you don't make any mistakes, the hints are perfect. Then it turns out that you don't really need to know the entire sequence to compute the offline optimum. You can just do it in an online fashion, as long as I know exactly when it's going to appear next. The Bellardi rules applies actually. But if the hints have errors, Theodoros and Vasilevsky, and followed up by a bunch of work by Alex Way and Dhruv Rothke, they studied this problem of caching with hints and have got a bunch of like very nice results, trading off both robustness and consistency. Okay, so they're all robust, they're all consistent, pretty much everything is tight, I believe, but they're not parsimonious. They kind of require the hint at every time step. And that's exactly the question that we address. So we ask, can you get away by not asking for hint at every time step? Can I ask for hint only when I need it? Okay. So to introduce this, let me quickly go over the marking algorithms for caching. I'm sure most of you know all these things. So it's just an analysis framework that helps study these algorithms in a unified way. So the algorithm setup is very easy. So you initially, it kind of proceeds in phases. And in every phase, the beginning of every phase, all the pages are unmarked. Whenever you fetch a page, you mark it. And if you have to evict somebody else, then you picked one from the unmarked pages in the cache and then you kick them out. Right? So the interesting thing is that this framework can capture deterministic and randomized algorithms for caching. The main here is how do we specify evict, right? Everything else is fixed here. So if evict is randomly chosen, then you can get a log K comparative algorithm as an old result. So now we'll try to take this evict black box and try to make it parsimonious. That's the whole goal here. Here's a naive way of doing it. If the cache has, so let's epsilon be some parameter, right? If the cache has epsilon times k unmarked pages, that means there is a lot of unmarked pages, then you do as before, just return a random unmarked page and be done with it. But if the cache has fewer than epsilon k unmarked pages, you query its next arrival time using the oracle, and then apply Bellardi on whatever you have. Right? So it's an interpolation between Bellardi and offline algorithm. So here, no, for simplicity, I'll assume that the hints are correct. Hints are good, actually. No, there are no adversarial hints, but you can extend it to the adversarial case. So what I can show is that for any sequence P, this algorithm uses epsilon times P hints because you only call the oracle only when the cache, the number of unmarked pages in a cache gets less than below epsilon, and then it achieves like a log 1 over epsilon comparative ratio. But it's still like linear number of hints if you think about it, right? Because it's epsilon times length of the sequence. Okay. So we can actually improve on that. So here's another algorithm. It's again like specifying only the evict black box. So it samples B pages from the cache, say without replacement. And then for these B samples, each of the samples get their next arrival time or get the hint, basically ask the hint for when is this page from the sample going to arrive next. And again, apply Bellady on this, whatever you obtain. It turns out that this one gets you a lot more elastic relationship between the number of queries and the competitiveness of the algorithm. So you can show that you get like log k to the base b competitive algorithm, which makes at most b times this quantity times opt many queries. So if the opt is really well behaved, the number of cache misses is less than 1 over k to the epsilon, you actually end up with sublinear number of queries. The proof idea is based on Theodorov's et al. Work. It uses the eviction chains framework. I wouldn't go into the details. It's not very difficult, but it turns out that this actually is fairly tight as well. So the dependence on these things are fairly tight. You can come up with a worst case instance. The harder part is to, the lower bound is actually the tricky one, because you need to impose a sequence of simplifying assumptions about the algorithm. The lower bound by itself will not work. So you need to assume that algorithm has some property and then slowly narrow down to like a very special case. Okay. Now that I'm on time precisely, what's the conclusion? So we studied learning augmented algorithms that are parsimonious, that do not require hints or advice at every time step. I believe that this opens up a lot of interesting algorithmic questions to explore. This field has been developing at a rapid pace. And so you could study many of the algorithms through this lens of parsimony. Of course, I would like to get more practical applications. To date, I don't think this area has seen a lot of practical gains yet, or maybe they're not been applied at broad scale. So that we would like to change that. And I always put in a plugin for, this is a kind of a complexity class I would like to understand, study, propose, whatever you want to call it. It kind of brings both TCS and ML communities together with the superscript. Thank you.
So maybe let's take one or two big questions because those changes. One big question that I have about the casting problem, you still assume no leaves of question. So do we know whether it answers parsimony and also something I want to get adaptive on the errors?
We cannot assume that because we do, for every value of b, you get some bound.
But can I even extra strategy? Should that, I didn't get why that should also the number of questions you do depend on opt, right? Because
I'm giving you a recap of it, depends on entire sequence.
okay, so it would be like epsilon k times opt.
Yeah, something. Yeah. What is the linear?
Sure. Okay.
Other big question. The 10 have a very